Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, glad to be back. Exciting topic today, I think.
Hopefully more exciting than the last one. Always good to be here.
Yep, ready to dive in. Let's see what interesting ideas we can unravel this time.
All right, so today we're looking at this new paper. Let me just pull it up. Okay, it's called Robust Autonomy Emerges from Self-Play. Basically, it's about training autonomous vehicles entirely in simulation, and they achieved some pretty impressive results, supposedly driving for like 17.5 years on average between incidents in the sim.
Wow, 17.5 years? That's significant. Self-play, huh? Interesting approach. So, no real-world data at all.
None, apparently. All generated in their GigaFlow simulator. They claim it can synthesize and train on the equivalent of 42 years of driving experience per hour, using a single 8 GPU node, which is just insane.
Okay, hold on a second. 42 years per hour? On one node, I'm immediately skeptical. What kind of fidelity are we talking about in this simulator? Because garbage in, garbage out is still a thing.
That's exactly what I was thinking. Simulation is great for initial training, but the real world is messy. Unexpected events, sensor noise, edge cases, all that stuff gets lost in a perfect simulation.
True, but the paper mentions state-of-the-art performance on 3 independent autonomous driving benchmarks, and supposedly, it outperforms previous models trained on real-world data, even when tested on recorded real-world scenarios. That's pretty compelling, even if it's just benchmarks.
Yeah, and the abstract also mentions it's realistic when assessed against human references. So, it's not just avoiding accidents, it's driving like a human would, at least according to their metrics.
Driving like a human. That's even more concerning. Humans are notoriously bad drivers. We get distracted, make mistakes, and are generally unpredictable. Do we really want to emulate that in autonomous systems?
Well, I think the idea is to mimic the naturalness of human driving, not necessarily the errors. Things like anticipating other drivers' moves, navigating complex intersections smoothly, stuff that current self-driving cars often struggle with because they're too rigid.
Exactly. It's about blending in, being predictable to other drivers so they can anticipate your actions. Otherwise, you end up with these overly cautious, jerky movements that actually increase the risk of accidents.
There's definitely something to be said for that. But Sarah's point is valid too. How do we ensure the system is learning the right lessons from this simulated human behavior? What's stopping it from picking up bad habits?
That's where the self-play aspect comes in, I think. The cars are essentially competing against each other in the simulation, constantly pushing each other to improve. It's like an evolutionary arms race, where the best driving strategies emerge over time.
Self-play works great in games like Go, because the rules are clearly defined and the goal is unambiguous: win the game. But driving is much more complex. The rules are often implicit, and the goal is multifaceted: be safe, be efficient, obey the law, don't annoy other drivers. How do you encode all that into a reward function?
And reward functions are notoriously difficult to design. If you don't get them exactly right, you can end up with unintended consequences, like a car that avoids accidents by just sitting still, or one that prioritizes speed above all else, even if it means cutting people off.
Yeah, reward hacking is a real concern, but the paper claims the system achieves unprecedented robustness. 17.5 years between incidents suggests they've managed to mitigate that, at least within the simulation.
It's all happening in the simulation. Maybe if the simulation doesn't include enough edge cases, the car will drive poorly in real life.
I'm still not convinced that deep learning is the right approach for autonomous driving, period. I think we need more neuro-symbolic systems, something that combines the pattern recognition capabilities of neural networks with the logical reasoning of symbolic AI.
I agree with that. Deep learning is impressive, but it's essentially a glorified curve-fitting exercise. It doesn't really understand the world in the way that humans do, and that understanding is crucial for dealing with unforeseen situations.
Okay, but where are these magical neurosymbolic systems? We've been talking about them for decades, and they're still mostly theoretical. Deep learning is delivering results now. This paper is proof of that.
There's a really interesting point to be made here. Imagine combining the strengths of deep learning with insights from how the brain processes spatial information. We know the brain uses things like grid cells and place cells to create a cognitive map of its environment. Could we somehow integrate those neural mechanisms into the AI's architecture?
That's closer to what I'm imagining. We need to move beyond just throwing data at neural networks and hoping they learn something useful. We need to actively engineer in representations and reasoning mechanisms that are inspired by how the brain actually works.
Absolutely. And I think a key aspect of that is spatiotemporal reasoning, the ability to understand how things move and interact in space and time. Current AI is still very weak in that area. It's like it exists in a series of disconnected snapshots, rather than a continuous, dynamic world.
But wouldn't that require a massive overhaul of current deep learning architectures? We're talking about fundamentally different approaches.
Maybe, maybe not. There might be ways to augment existing architectures with neuro-inspired modules, like a separate module for spatial reasoning that interacts with the main deep learning network. Think of it as adding specialized hardware to the system.
That's interesting. So, you're thinking of a hybrid system where the neural network handles the low-level perception tasks, like object recognition, and the neuro-symbolic module handles the high-level reasoning and planning?
Exactly. I think the key is to find the right division of labor between the two. Let the neural network do what it's good at, pattern recognition, and let the neuro-symbolic module handle the more abstract reasoning and decision-making.
And the neuro-symbolic module needs to be able to translate between different coordinate representations. That's crucial for spatiotemporal reasoning. The ability to map the world from different perspectives and understand how those perspectives relate to each other.
Okay, I'm starting to see where you're going with this. But how do you even begin to design such a system? Where do you start?
Well, I think we can draw inspiration from neuroscience. Look at how the brain represents space and time. Look at the neural circuits involved in navigation and motor control, and try to translate those principles into algorithms and data structures that can be implemented in AI.
And don't forget the importance of symbolic knowledge representation. We need to be able to explicitly represent concepts like lane, intersection, traffic light, and the relationships between them. This is where symbolic AI can really shine.
And the system needs to be able to reason about those concepts in a logical way, to infer new information from existing knowledge. Like, if the traffic light is red, then I need to stop. That's a simple example, but it illustrates the power of symbolic reasoning.
So, you're envisioning a system that combines deep learning for perception, a neuro-inspired module for spatial reasoning, and a symbolic AI module for logical inference. It sounds incredibly complex.
It is complex, but I think it's the only way to achieve true general intelligence. Deep learning alone is not enough. We need to combine it with other approaches.
I completely agree, and I think this paper, while impressive in its results, actually highlights the limitations of a purely deep learning approach. It shows that you can achieve good performance in a simulated environment, but it doesn't necessarily translate to real-world understanding.
And it reinforces my belief that spatiotemporal reasoning is a crucial piece of the AGI puzzle. We need AI that can understand the world as a dynamic, interconnected system, not just a collection of static images.
Okay, you've convinced me that neuro-symbolic approaches are worth exploring, but I still think deep learning has a lot to offer. And this paper shows that it's making significant progress in autonomous driving.
Absolutely. And I think the key is to find ways to integrate the best of both worlds, to combine the strengths of deep learning with the insights from neuroscience and symbolic AI.
So, what are some specific research directions that could come out of this discussion?
From my perspective, I'd love to see more research focused on the underlying neural mechanisms that drive geometric reasoning in humans. Things like how the brain represents spatial relations, how it performs mental rotations, how it solves geometric problems. And then, try to integrate those findings into the design of AI algorithms. A combined approach could lead to more robust and adaptable AI capable of truly understanding spatial relationships.
I'm really interested in the generalizability of this approach. If this model excels at geometry, how transferable are the underlying techniques to other problem-solving domains? For example, physics or complex engineering designs. That's the real test of whether it's just solving a particular problem or something more profound.
I'm concerned about the evaluation metrics. The gold medal performance emphasizes performance above true understanding. We need more robust, symbolic evaluation methods that aren't susceptible to hidden biases in the data. How can we formally verify the reasoning capabilities of these systems instead of just relying on benchmarks?
I'd like to see more research into non-Euclidean coordinate representations. This system seems to be confined to 2D/3D geometry. How can we develop AI that can handle more abstract spatial relationships and translate between different coordinate systems? That, I think, is key to achieving true spatiotemporal reasoning and AGI.
And thinking about the simulations, how much simulated variability is really needed for real-world robustness? Is there a point of diminishing returns where adding more simulated scenarios is not worthwhile compared to the cost and computational resources required?
That is a great question. I wonder, how does this system handle situations where there are multiple possible solutions? Does it just pick one at random, or does it somehow explore the solution space and find the optimal solution? Neuroimaging data could provide clues on that.
It's more than just solutions. How does it represent uncertainty? The real world is full of ambiguous situations where there's no single correct answer. How can we design AI that can reason about uncertainty in a principled way and make decisions even when the information is incomplete or contradictory?
And how does it handle the flow of time? Does it just treat each moment as a separate frame, or does it have some way of tracking changes over time and predicting future states? That's crucial for anything that involves planning or decision-making.
And how is knowledge represented and reused? Is each problem solved from scratch, or does the system learn from its past experiences and apply that knowledge to new situations? Transfer learning is a big deal.
Following on transfer learning, how well do the latent tokens, the compressed representations the system uses for reasoning, compare to actual neuronal firing patterns during complex tasks? That direct biological comparison could lend real credibility and insight into their utility.
Yes, there is something important to consider. Can we define a set of basis functions to represent the geometry, something akin to Fourier analysis but for shapes? We can encode these shapes that the system identifies within the latent space to see if it matches up with the system. This will test true understanding.
Extending the coordinate system idea. What if the latent tokens could be used to dynamically adapt the coordinate system based on the problem at hand? Like switching to a polar coordinate system for dealing with circular objects, or a different projection for navigating complex landscapes. That would be a powerful way to achieve truly flexible spatiotemporal reasoning.
All very interesting points. It's clear that while this self-driving research is a significant step, it also opens up a whole host of new questions and research directions. I think it showcases the potential of deep learning, while simultaneously highlighting its limitations and the need for more sophisticated approaches.
Yeah, it reinforces the idea that AGI is not just about scaling up existing techniques, but about finding fundamentally new ways to represent knowledge and reason about the world.
And it reminds us that we need to be critical of the metrics we use to evaluate AI systems. Performance is important, but it's not the only thing that matters. We also need to consider things like robustness, explainability, and true understanding.
And it underscores the importance of spatiotemporal reasoning as a core component of general intelligence. We need AI that can understand the world in a dynamic, interconnected way, not just as a collection of static snapshots.
On the topic of knowledge, are the latent tokens actually encoding knowledge, or are they just encoding statistical correlations? How can we determine what they actually represent?
That's huge, isn't it? It goes back to the fundamental question of what it means for a machine to know something. How do we distinguish between genuine understanding and just clever pattern matching?
That's why I think the ability to extract explicit roles and relationships from the latent space is so critical. If we can translate those hidden representations into something human understandable, then we can start to assess whether they actually capture meaningful knowledge.
And maybe that's where the neuro-symbolic approach can really help, using symbolic AI to explicitly represent the relationships between different concepts, and then using the latent tokens to ground those concepts in the real world, a bridge between the abstract and the concrete.
I think that with further improvements to model efficiency, especially with latent tokens and other compression methods, we will see continued progress toward artificial general intelligence over the next few years.
That is an excellent point. I see this as another piece of the puzzle, showing the power of combining computation with biological inspiration.
It will be really interesting to see how the next few years play out, whether deep learning remains dominant or whether neurosymbolic approaches start to gain more traction.
Only time will tell, but I'm optimistic that we're making progress towards AGI, even if it's not always in the direction we expect.
One thing's for sure, it's an exciting time to be working in this field.
Absolutely. All right, I think that's all the time we have for today. Thanks for joining us, everyone.
Yeah, thanks for the discussion.
See you next time.
Bye, everyone.